6. So it's expected to finish before 1 o'clock. So I will try to finish earlier than that due. Actually, I prepared 3 lectures for today, and lecture 4 is a little bit longer than other 2. Okay? So be patient about the first lecture. The lecture 5 and 6 will be shorter than this. Right? This composite material constituents today. We look a little bit the more detailed manner. So, maybe do you have a pointer? No. About reinforcement, shape of string. Actually, there are except glass fiber, but glass fiber is very common. Although it is one of advanced fibers, but because it is very common and relatively very the less satisfactory performance compared to other fibers. Other fibers are carbon fiber or aramid fiber. So, about the fiber, I will focus on the carbon fiber and the aramid fiber. In addition to those, I introduce about the natural fiber. Okay? So, 3 of those. Firstly, the carbon fiber. Carbon fiber is composition and structure and possibility. In this viewpoint, composition is a very thin and strong crystalline filament of carbon atoms. And the structure is a filament bundled into tow and woven into fabrics or sheet. So that means a single wise carbon fiber will not be used. It will be bundled. And that bundle is implemented or so it is woven into fabrics as a preform, something like that. That kind of the reinforcement structure is usually used. And the versatility is it can be easily molded into various shapes while maintaining its strength property. That means it is very free to be applied with various manufacturing process. Actually, this development is very long back, more than 100 years ago. That means it is not new fiber. It is not new fiber. That's okay. Thank you. So going back to 1860s, it was firstly the developed so-called carbon fiber. That is carbon fiber was for incandescent light bulb purpose. So this Joseph Swan, this guy got the idea if he burn the fire or the paper, they could say because that paper is carbonized, because after burn, that will not be burned again. So it can be used for very high temperature the incandescent light bulb purpose. So it was purpose. So that means the first generation of carbon fiber, it is not for strong strength reinforcement use. So that means it's very weak, much weaker than ordinary material, but it is the form of carbonization. So that carbonization is about less than 40% of that volume. Compared to these days advanced carbon fibers, its carbon content is more than 92% through 99.5%. Okay? So it's very different from these days carbon fiber. But anyway, it started from these days. And in 1960s, this is origin of modern carbon fiber development. And it's in these days, although union carbide is developed well, but mostly advanced the manufacturing technique for obtaining carbon fiber was developed by Japanese. So that's why still the best carbon fiber company is Japanese industries. Its the name is Toray. Toray is #1 carbon fiber manufacturer these days. And they developed many patents since 1960s, and to present the continuous improvement in strength, modulus, manufacturing process means they wanted to increase the percentage of carbon in final form. It's from first 30% to 99% these days. So key property of carbon fiber is, of course, strength is very required. So extremely high tensile strength is surpassing at least 4 times or 5 times compared to the steel. And the weight is very light. So its the weight is density is one half of steel, and stiffness is very high modulus of elasticity and excellent rigidity. That means its specific strength is very enormously high. You will see the number after this. And about its manufacturing process, it's starting from precursor preparation. That this is one of very common the precursor used to make a carbon fiber. So PAN is polyacrylonitrile, or pitch. We say pitch as a starting material, and oxidation process is needed so that the fiber, the precursor, is heated in air and to stabilize its structure. And the carbonization process, in this process, high temperature treatment in inert atmosphere remove non-carbon atoms. So this is a very important process, so that the contents of carbon can be greatly improved. And after that, surface treatment is needed, because according to the surface treatment types, its strength can be influenced greatly. So this is one of carbon fiber produced by pyrolysis of silk cocoon. Silk cocoon is formed, and this is the carbon fiber. It can be used for carbon fiber or the raw materials. So it will be treated after this. So this is size is 0.1 mm. This is 100 microns. So you can see that its diameter thickness it looks like about 10 microns, something like that. So usually, advanced carbon fibers, it has 5 to 10 micron in diameter, very thin. And there's it's a carbon fiber type. It's modulus and the intermediate modulus, high modulus. That means this is different type of carbon fiber. Okay? So standard modulus is a common, the regular one of carbon fiber these days. It has tensile modulus is about 230 to 240 gigapascal. That means it can be compared to the steel. Steel case, it's the tensile modulus is 200 or 210 gigapascal. That means it is slightly higher than regular steel, but intermediate modulus is greatly increased, and the high modulus case is almost 2 times of standard modulus. And typical applications, so high modulus case is because it's very stiffened one, so satellites or high-end racing is used, made of this one. And the aerospace industry usually intermediate the modulus. And in a living environment, sporting goods or automotive, it's used standard. So there is one more ultra high modulus, it's UHM usually we say. So UHM case, it's a tensile modulus up to 900 gigapascal. So this is a map of carbon fibers, tensile strength versus tensile strength. Okay? So that means this is steel. Okay, steel. Most other, so aluminum or other metals here, and this is carbon fiber. This is carbon fiber. This is carbon fiber. Good. These are carbon fibers. Okay? That means this because this is a steel or steel elastic modulus level. So this is a very high. This is about ultra high modulus type, right? But this is standard type, right? Here. And this is tensile strength. Tensile strength is this is 3,000 megapascal. That means if you see just carbon steel, that is around the 700 megapascal also. That means you can see that it's a very highly the tensile, very high tensile strength zone is occupied. Right? So this one standard type. So from this is standard modulus HS is this one, and the intermediate modulus one is this is a standard one. This is intermediate one. This is a high modulus one, and this is ultra high modulus. And that means ultra high modulus has much lower than the standard one or intermediate product. It is not linearly related. So this is a more detailed numbers. This usually a carbon fiber, its grade is rated by using symbol T700, T800, T300, something like that. So that grade is, for example, this is a group of T700. It's the tensile strength range is about 4,900 megapascal. Okay, it's a tensile strength and something like that. So, and the 800 rated one, T800, you can see the more higher than 5,000 megapascal level. You can see, and there is the highest one is T1100. T1100 is a 7,000 megapascal level. So enormously higher because T1100, the rated one is 10 times stronger than steel. So the symbol has number 700, 800, something like that. There is some different interpretation why those kind of terminals are used to symbolize each the differently rated carbon fiber. So you can see like this. For example, 4,900 megapascal. 4,900 pascal is for T701, right? T701. If you change that megapascal into kilo psi, kpsi, in that case that is 710 kilo psi. That means around 700, right? If you see the 800 rated one, then it's about 50 is 700 megapascal. If you convert it into KSI, then you can see the 796. That means it is about 800. So that level is the origin of the name of differently rated carbon fiber. Anyway, so currently, so mostly the cheap and the most widely used one, T300. And a little bit advanced product, so stronger one and the very light one. Usually we use T700, but it's a very extremely high level product, like the mostly advanced component of the aero bicycle, something like that. The case they use T800. Very, very expensive. In the case, if just one small compartment can be 1,000 US dollar. So it's very expensive. And T1100 is rarely used except highly targeted product. So the carbon fiber reinforcement, if we use those kind of material, then lightweight is required. So, and high strength, and corrosion resistance, and fatigue resistance. So this all for weight and strength and corrosion resistance, durability is mostly required performances from modern machine parts or the structures. So carbon fiber can satisfy easily to engineering need, except cost. So the carbon fiber are widely being used in these days, but only one constraint was cost. But even in that case, so some of the advanced users seek to buy the carbon fiber based computer for their use. So that market is rapidly expanding these days. The carbon fiber the composite based on in aerospace is mostly used here. And the sports equipment also used because the end users for aerospace flight was sports equipment in high-end case. In the case, they don't mind about the cost of product. They just wanted to get performance. So T800 or T700 is usually used for this. But automotive cannot use T800 except very inevitable situation. So if automotive compartment to use the fiber, that means T300 is mostly used. And the wind energy case is because wind turbine blade is very long, it's longer than 50 the 50 meter to 100 meter, so very, very long. So it must be lighter and it should be very strong. So the wind energy, they use very highly rated one sometimes. And so the carbon fiber also have a challenging point and its limitations. The first one is cost, of course. If cost can be down, then so maybe it can replace most of steel, the machine components, but the cost cannot be easily down. So cost case, high production cost limit widespread adoption in many industries. So this is one critical issue. And another one is compressive strength. So, the tensile strength is needed for most of structures, but sometimes the compressive stress dominated structure is also the incompressive strength is much lower than tensile strength performance. So lower compressive strength than tensile strength, so requiring careful design consideration. It is not equal. It is not equal. And the impact resistance is poor performance. That means very rapid impact environment exposed, because this will be severely damaged and it should be replaced many times. It is very difficult to be fixed. It is not partly, sometimes so some kind of fixing process can be possible, but in serious situation, even there is a small damage, it's advised to replace the whole structure. That means its cost cannot be imagined. So that is one of very difficult target to overcome. The carbon fiber recycling and the sustainability issue. So carbon fiber is collection and sorting and reclamation and reuse. All of things is possible. And about aramid fiber. Compared to the carbon fiber, aramid fiber has different performance that carbon fiber doesn't have. And the unparalleled performance characteristic from aramid fiber is the finding more applicable the market these days. So this aramid fiber is defined as aramid fiber type of synthetic. This is a synthetic one. Synthetic one is a chemical process we designed. But carbon fiber case, we just pyrolysis is needed. So it is not, in the sense, not the synthesis. This aramid fiber is synthetic and the aromatic polyimide, known for its high tensile strength and heat resistance, like carbon fiber. But its origin is developed only 1960s firstly, and it was pioneered by DuPont company. So after patented by the DuPont could get a huge market by using this aramid fiber. And also the other competing companies have successfully patented with a little bit different style of aramid fiber. So its application is aramid the fiber is widely used in industry from aerospace, automotive to sports equipment. So very similar to carbon fiber, but it has different the markets compared to the carbon fiber. So molecular structure and the property of aramid fiber is molecular structure is a long polymer chain with a unique aromatic polyamide structure. So it can give it remarkable strength and thermal stability. This is very important for aramid fiber. So this thermal stability is very important characteristic that aramid fiber can show. And the key property of it, high tensile strength, like carbon fiber, heat resistance is better than carbon fiber. Chemical inertness and low density, like carbon fiber. So it's very similar properties can be found from the aramid fiber. And the customization is very easy. So its aramid fiber application can be expanded further. So in 1960s, aramid fiber was developed DuPont, and 70s commercialization was engaged, and up to today, the continuous advancement in fiber technology. So we are still having the improved property and the expanded application from aramid. So key application of aramid fiber is aerospace, automotive, personal protective gear, and sports gear. So especially this is different from carbon fiber. Right? So lightweight, high strength. And this is exceptional heat abrasion resistance. This is very important performance from aramid. And the automotive is aramid fiber reinforced tire and the brake pad and the other critical automotive parts. They are using aramid fiber for reinforcement, and the sports equipment is a high strength to weight ratio of fiber can enhance performance of sporting goods, etc. So this aramid fiber, we say it is gold fiber because its color is yellow. So aramid fiber, its composite, it looks like yellow. And manufacturing process aramid fiber is polymerization is the first step, and then spinning and the stretching and heat treatment process needed, and the finishing. So each process is very lengthy to introduce here, and there is so many different variations. So it's difficult to summarize here simply. And aramid fiber in composites, it can show the exceptional strength. So fiber high tensile strength to weight ratio. So it's much higher than other composite material except cis composite carbon fiber composite materials. And the dimensional stability is excellent. Low coefficient of expansion. This is a very important performance can be obtained from aramid fiber composite as well as carbon fiber composite. Carbon fiber composite is virtually zero thermal expansion coefficient. So that means that its dimension, outer dimension, will not be influenced severely by temperature change. It means after manufacturing, even at high temperature use, its overall shape and the dimension will not be influenced. That means it is very unique characteristic and necessity. And thermal stability. So aramid fiber inherent heat resistance make it suitable for use in high temperature applications. That means it can be used for the fire protection industries. And the chemical resistance also excellent. It exhibits the excellent resistance to solvents, acid, and other chemicals. So even those kind of toxic chemical environment, it can survive for a long time. Okay? The comparison to other reinforcement materials, there are glass fiber, very commonly used one, and carbon fiber and steel, something like that. And glass fiber case, aramid fiber offer higher strength to weight ratio compared to this one, almost 10 times compared to glass fiber reinforced polymers. But its strength is equivalent or a little bit inferior than the carbon fiber reinforcement. Challenge and limitation of aramid fiber. Aramid fiber, so damage susceptibility, cost consideration, recyclability concern, fiber matrix bonding should be considered when you choose the aramid fiber as a reinforcement of your composite. So damage susceptibility means it can easy to damaged from the abrasion, impact, and certain chemicals requiring careful handling. Those kind of environment, this aramid fiber composite can give excellent performance. The cost consideration should be concerned. It can be calculated, estimated easily from the market element, the list. So whenever you want to use aramid fiber, it can be considered reasonable compared to the carbon fibers. Because carbon fiber T700 or T800 is enormously expensive, so it cannot be used easily. But this aramid fiber reinforced composite can show the equivalent but slightly lower than the carbon fiber, but it has its own the strong performance too. So the aramid fiber can be a first candidate before prior to carbon fiber of choice. So emerging trend and the future outlook. So aerospace innovation. So ongoing development of lightweight, high performance aramid fiber composite to next generation aircraft and spacecraft. This kind of outlook is very prevailing, and the automotive lightweight trend can be advanced by using this kind of composite. And the healthcare application, also medical device or prosthetics or protective gear for healthcare professionals is usable and a sustainable solution also. So carbon fiber versus aramid fiber. So application field issue. The carbon fiber is a new type of fiber material. Its carbon content is more than 95%. 95%. So carbon fiber is black gold. Its color is black, but here is gold means this can be a very, very excellent component for obtaining the desired performance, except cost, of course. So this carbon fiber, its value price very high. It's a problem. It's mainly used in aerospace, national defense, military workers, because these areas, the product price is not so difficult issue. So performance is more preferred. So that's why carbon fiber can be used easily these areas first. And the increase in production capacity of large wire carbon fiber is so tried these days. So some more application fields, including the civilian field, is increasing. Whereas the aramid fiber is a synthetic fiber, as I said, and it has characteristic high strength, high modulus. Sorry, it's a high modulus, and it's commonly used on bulletproof products. So aramid fiber is mostly used uniquely in bulletproof products, and construction materials, special protective clothing, and electronic equipment can be used. And mechanical property issue, T300 carbon fiber is stretching to about 3,000 megapascal, and elastic modulus is 225 gigapascal level, and breakdown rate is 1.7%, density is 1.77 gram per cubic centimeter. That means about 1/7 of steel. And a T1000 carbon fiber performance case is stronger than T300, and higher modulus than high strength compared to T300. But the aramid fiber stretching strength is about 3,000. So T300 carbon fiber has the comparable strength with the aramid fiber, but its elastic modulus, this aramid case is about half of T300. Right? So that means that this stiffness is about half compared to. So strength case, the carbon fiber is superior, but the cost and the thermal stability case and kind of to say is energy absorption ability. So in those kind of case, aramid fiber is better than the carbon fiber. So thermal stability. So aramid fiber is very good to thermal stability. So for example, it can suffer from if there is no decomposition, then it can be used. For example, at 180 degree temperature environment, the aramid fiber reinforced composite can sustain long time, and at 150 elevated temperature, it is very good survival, and the temperature expansion coefficient is about -2 times 10 to -6. Okay, that's very low, and the carbon fiber case is lower than the aramid thermal expansion coefficient. This is for T300, so almost virtually zero. Okay, means the thermal chemistry case carbon fiber. Carbon fiber is similar to carbon, and oxidized strong oxidant, so inert with general alkali. Okay? And temperature up to the 400 in the air. So obvious oxidation can be occurred more than exceeding 400 Celsius, exceeding in the case of CO and the CO2 generated. So carbon fiber has good corrosion resistance, something. Okay? And aramid fiber easy to erode by various the pitch and the erosion of strong acid. So in the case it is not good. So you see the aramid process. It's a typical process. You see, this is carbon fiber, the manufacturing process. So this case, the precursor is make the tensile drawing. So to get the continuous the carbon fiber, it's along this process, it's the diameter is reduced and reduced gradually. So that means the final diameter is up to 5 micron to 10 micron in diameter. Okay. So if you have any question, you can stop me at any time. Because, actually, I'm very interested in the calculation, usually designed by computation. So this kind of just background information is just needful information to choose this element for this structure, something like this. So there is no special emphasized points for this or for that, and something, because needed one is just a comparison table actually. But these days AI-based question window can ask and to choose as you wanted to have. Any kind of engineering data can be compared directly. So this kind of overall background information is very boring many times. So I believe you would feel some kind of boring about hearing this kind of background information. But so if you have any project or business based on this kind of advanced composite, this kind of information you should be exposed at least minimum level, at least. So although it is not interesting, but you need to the review at least 1 or 2 times. So if you have any question about practical run, something like that related to this, just anytime you can start me. So advanced fibers up to 2010, up to around that time, only the high strength and high durability, those kind of manufacturing process and choice of composite constituent pairing were main issue to be researched. So a series of tests and the estimated the strength or lifetime based on your the collected data, those kind of things always needed. But I believe it was around 2010. So recycling issue, also eco-friendly issue, or abruptly emerged from various advanced, developed countries. That means because developed countries, this kind of composite material should find its market. Otherwise, there's no way to sell those kind of products because those are very expensive. So if there are government-based policy from developed countries which have most of advanced composite markets, so require, okay, that must be recycled first, otherwise it is limited. Those kind of political issues were introduced to the development of composite materials. So it's a matrix case, Somerset polymer. It's encountered very difficult situation because it cannot be recycled. And the fibers, sometimes the fiber cannot be recycled. So alternative way to replace uncycled the fibers, advanced fibers which cannot be recycled is to find from natural fiber, from the nature. So since 2010, around that, in academic society, we can encounter many times about this newly processed the natural fiber from some existing nature, something like that. Those kind of natural fibers were introduced after that. So these natural fibers as a sustainable source and diverse availability, unique properties, those can be satisfied by choosing most of natural fibers. Different categories of natural fibers we can find. So plant-based fiber, this is the most common case. The plant-based fibers, natural fiber can be derived from stem, leaves, seeds of plants, or to flax and cotton. Those kind of things or resources to get natural fibers. So different category can be found from animal-based fibers. This case of fiber obtained from animal source like silk, wool, cashmere. And the mineral fiber, so fiber made from naturally occurring mineral, asbestos or glass. So these natural fibers have, of course, it has advantages as sustainability. It's renewable and biodegradable. Okay? So that means it is so politically required eco-friendly issue can be overcome. So this natural fiber became a very important new fiber group. And it's relatively, its price is very low compared to artificially developed advanced fibers. According compared to that, is collected from nature. So natural fiber generally less expensive and to produce than synthetic alternatives. Right? But and density is very low. Natural fiber have a lower density compared to glass, carbon fiber, because this kind of fibers should be found from living things. So to support its living lifespan, so the constituent as a body must be light is very needed to overcome gravity. And the customizability as a property of natural fiber can be tailored from various processing techniques. It's compared to the artificial ones, it's very easy to process. But also has disadvantages too. There is an inconsistent quality, so there's a much spectrum of qualities, differently from artificial ones. So it is not uniform. So natural fiber can exhibit more by variability in their property compared to synthetic ones. So there's ununiform qualities are one problem issue, and the second one is moisture absorption is best because it's from mostly living things. So this is one more problem. And the low thermal stability, of course, is very the weak to the fire, something like this. So it is not suited to the high temperature use. That's problems to be overcome. And the chemical composition of a natural fiber is mostly cellulose based. And the hemicellulose, lignin, is beyond the research scope, so I have no deeper idea about that. But usually I can see the cellulose-based natural fiber is mostly accepted. And structure and morphology of natural fiber, cellular structure, microfibrils, surface characteristics, those kind of things can be observed from natural fibers. So just testing-based information collected to make a list so that it can be used to choose any kinds of fiber will be chosen for this composite, something like this. So its list is very messy, very best. So because artificial fiber case, we have a very well-defined ones. So we can choose very detailed numeric qualities can be found. But these natural fibers, it has a wide range of and ununiform properties. So many times just the medium value should be used. So it's very difficult to choose as a mass production. Yes. And the surface treatment of fiber is usually needed to get better performance, not just natural fiber itself. So in order to get chemical modification or physical modification, coupling agent, those are used frequently. So chemical modification is treatment like alkali, silane, acetylene, thalation, and can improve the fiber matrix adhesion. So to improve that manufacturing the performance, there's chemical modification usually used. And the physical modification is the plasma corona treatment. So used to change the surface energy of fibers. So that means surface is very important issue because it must be contact with the matrix in the composite. So treatment of surface at any chemical or any physical, any the roughness condition, those kind of all influence the property of composite eventually. And the coupling agent, to use capital compact catabolizer, creates a covalent bond between fiber and matrix, those kind of. So to make a composite performance as desired, those kind of treatment are needed and adopted. So application of natural fiber in composites is usually all fields can be possible: automotive, furniture, construction, packaging, but it has limitations according to its intrinsic property. Right? And the challenge and the future trend, and of course this natural fiber will be finding more usability eventually, because we wanted to get environmental conservation, something like this. So not an engineering issue. It's because it's from the social issue. So it will be more emphasized in composite society. And nanoparticle reinforcement is one other very important reinforcement form, differently from fiber reinforcement. So nanoparticle is because this kind of reinforcement is well attracted. The reason is it is very easy to handle in industry, and it can effectively change the property of composites. And there are many kinds of particles can be used. So it is very the potential reinforcement. Okay, and differently from fiber, it is not a kind of preform shape. It is not needed. It's just mixed before starting manufacturing. So it's very easy to use. Okay? But it has a very difficult situation due to its advantage. Because it's a mechanical, thermal, electrical, it can all support the final composite performance, but it has some the problems to overcome for the mixing as materials. Agglomeration should be it is to prevent from the manufacturing, right? The manufacturing composite materials, so it must be resolved, right? And the compatibility issue, right? Because achieving good interfacial bonding between nanoparticle and the matrix material is very important, and the processing. So its kind of agglomeration must be dispersed. So improving the interfacial bonding with the nanoparticle, surface modification technique, and the coupling agent dispersion technique needed in that composition industry. And few application example is already we can find some kind of industries and products already. Its nanoparticle reinforced composite has so mechanical property, electrical performance, durability. Those kind of things can be easily improved by our desire. But limitation is dispersion challenge, health and safety. This is the most unknown issue. This is very unknown issue because a nanoparticle is very small, so it can make a good effect on composition to get desired property, but because it is too small, so it is very easy to inhale, And once it is go into your lung, nobody knows what kind of thing happening after 10 years, 20 years. So this inhalers and it's exposed to certain nanoparticle. In the case, the health problem can be caused. It's an unknown issue. So that is most difficult situation to persuade community. So this is very difficult issue. This portion, this is for manufacturing. This is for real use. Okay? And the environmental, the impact is a long-term environmental effects, nanoparticle in composite material is unknown yet. Unknown. So very easy to use for enhancing the performance based on various particles to be chosen for according to our desire, but its effect has not been known yet. This problem. So and, can be skipped. So this is 1 hour. Lecture is finished. So do you have any question about that? Very boring contents. That's right. So I'm sorry about that. But as I said, this kind of basic fundamental background information is not avoided. Okay? You need a minimum level of information. So because we have a second the lecture 5 and 6 after this, so at that time we can have more questions if you have. Right? So this is the end of lecture 4, and we'll get some the recess, and I'll come back after. Right? Thank you.